We now introduce a new idea, an enhancement of the model that allowed the encoder-decoder architectures to overcome some of the pitfalls and improve their performance. Let's talk about attention. We have seen as in encoder-decoder models, the issue we have is that especially when the sentence to work on, the sentence to encode, maybe to translate, when this sentence is very long, the problem is that when we reach our final state of the encoder and we compress all the information in one single vector to be passed to the decoder, somehow the beginning of the sequence is faded, is lost in the context, in this compressed vector. So the first idea is, instead of passing to the decoder just the final state, why don't we give all the states that derived in the RNN from processing all the symbols in the input sequence. And this is not a completely new idea. This has been done and tried before. Of course, that means passing to the decoder much more information, which the decoder may have a hard time figuring out where the relevant meaning and relevant representation is to find the most useful to generate the output sequence. And this is where the second idea comes from, because attention, if we look at the animation on the bottom, starts from the idea that when we generate an output sequence, for each of the output symbols, we have some of the input symbols that are involved more than other for this particular output. So in the animation, we see that the blue lines have different thickness, and they represent the different relevant input words at each step. And attention tries to embed in the model a capability which, for each output symbol, points at the right input for that particular word that we are generating, for that particular best word that we are looking for. And the approach it takes, of course, is the approach that we have already seen before and that we have talked about. The approach is to design a neural network model. For this, with some matrices of weights, with some parameters, and let the model learn the proper structure of these blue line connections by itself during the training. Let's start seeing how our attention model fits within our encoder-decoder architecture. Here we have our encoder and our decoder. The picture is a little bit different, but we can recognize on the bottom the encoder of our model, and the encoder has analyzed 4 symbols, and from each of the symbol we have a particular state that has been generated. And this state is deriving from 2 paths of the input data, one which is in forward and the other one which is backward. So we have a bidirectional encoder, and for each symbol we generate 2 states, and so we can stack these states together and have one total vector that we consider the state for that step. On the top, we see our decoder, and our decoder is working on generating output symbol. So we see here that the first output symbol has been generated, has been given as input to the next step, which is step 2. So here we have I equal 2, and we are in the process of finding this second symbol. And the input that we use to find the second symbol is, of course, the state from the previous step. But here we see also a new input, which here is called context vector. So what is this context vector? This context vector is the one that is generated by the attention mechanism. And the attention mechanism in generating this vector is taking as input the previous state, and which we call S of I minus 1. So here in this particular moment, it will be S1 because we are working on step 2. So we have the state that is coming from the previous step, and also attention is taking as input all the states of the encoder. Okay, so from these kind of inputs, we will now see how the attention mechanism derive the context vector to be fed to the RNN together with the previous state to calculate the new state and the output symbol for step 2. The first step that attention goes through is probably the most relevant, is the key step to derive the context vector. What we do, working on the previous state that somehow give us the information about the current processing we are doing on the decoder. So using this previous hidden state as input, the attention receives all the encoder hidden states. And for each of them, the attention derives a score, and the score represents a rating about this simple question. In working on this previous step, working on this previous state to generate the next state and the next symbol, how relevant is this input? This input has been rated 1.1, which is, let's say, medium compared to the others, while this input has been rated of lower relevance, and this input is the one that has been rated with the greater relevance. So how do these numbers get calculated? These numbers are calculated with a simple formula that is applied to each of these encoder states. So the encoder states that you are working on here is called HJ, where J is 1 here, 2, 3, and 4. And since we are doing this for all the steps here, we have another index which is I. So I at the moment will be 2 because we are asking ourselves what to do about the second step. So the score we get is a score for the second step of the decoder, and we go through this for each J of the encoder. And the way this is done is something that should be sound very, very familiar by now, because we said we have 2 inputs. One is the previous state of the decoder, and the other one is HJ, the state, that encoder that we are going to rate, to assess, to judge for its relevance. And what we do with the input, we calculate each of them, we project each of them with a specific matrix of weights. And of course, the same matrices of weights are applied to all the H, J, with J equal 1, 2, 3. So here, as we know, we get a vector as output, and as we have seen in previous occasions, the 2 vectors are sum element by element. So this element plus this one gives this element, and so on. So after we have these elements here, we pass this element through a nonlinear function, which we know also very well, and it's tan h. And so here we have a vector coming from here. So once we have a vector, we can multiply this vector by a matrix of weights which is composed of just one row. So actually this is not a matrix, but is itself a vector. And if we multiply these 2 elements, we do this first by this first, plus the second by the second, plus the third by the third, and at the end we get a single scalar number, which is a e I j. So at the end of all this process, we get a single number, and this single number is considered the weight of these encoder state, the relevance of these encoder states. To be stressed that the relevance is not coming from anywhere, but it is just learned by the model with giving the proper weights to this vector and these two matrices. So it will be the model trying to do the right translation, the right question answering, that slowly will adjust these weights, and the attention model will learn to put the attention and we learn to give the highest relevance to the most important input symbols in the input sequence. So once again, to be very clear, what is happening here and here is that what we saw before. We just have our inputs that are S, I minus 1 or Hj, and they get just projected using a matrix of weight, and we get another vector. What happens when we multiply this quantity, which is a vector, by this other vector, which is transposed? Transpose means that the vector is put in one row instead that one column. We have the situation where the matrix of weight is just one row, so we don't have this part. So we use just the first row by the input vector, and we derive the first number. So we don't have this, and we don't have this. So the result of this is our scalar alignment score that we are looking for. What happens in the picture is that we have this green box here. Okay, and the green box is this, projected by a matrix, and also the state which is taken at the moment as input, because we are applying this same to all of them. So the current encoder state is projected also, and then the two results are added up. They go through tanh, and then we have this VA transpose vector that, as we have seen before, give us a scalar number, and the scalar number is considered the alignment, the score, the rate, the assessment of how relevant this state is. The second step of attention is just a normalization of the numbers, because we want to put the numbers in a probability distribution, which means that first of all we want the total of our ratings to be a proper collection of weights and to be a proper probability distribution. So the main more relevant property is that we want the sum to be 1, as when we assess the probability of conflicting events to occur of different choices to happen, we want that at the end one of them must be the right one. So we want that the sum of a probability distribution, we want it to be 1. And the way this is obtained is using softmax normalization, which take the exponential of each of these input scores and divide it by the sum of these exponentials. But anyhow, what we must keep in mind is that now this is a probability distribution and the total is 1. Just as a reminder, the concept of attention had great developments and many proposals were made on how to calculate, and what we are showing this here is just the we can say the first approach, the original paper from Badenau and others, and we are showing a way to calculate attention that was proposed in that model, in that paper. And sometimes this is referred to as additive attention. And we must take into account that we may find around other ways to calculate. Back to our steps, we are now at the final step, which is step 3, to derive this context vector, which is our goal of all these mechanisms. And the context vector, now that we have the weights, so we know that this state must be weighted 0.2. We just multiply each of these vectors for its corresponding weight, and we obtain the context vector as the sum of these weighted vectors. So somehow at the end, since the total of these numbers is 1, we get what we consider one vector of these, but this one vector is obtained by taking 0.2 of these, and then we take 0.3 of these, and then we take 0.1 of these, and 0.4 of this one. So the formula is here. We multiply each vector by its weight, and then we just add everything up. We can now go again through the steps to give a little bit more details about the formulas for who is interested. And here we have, as we said, the score for the decoder step, we know I, and for each step we go through all the encoded states, which are scrolled through using index J. So for each guy of these we have J, and I is the one that we are working on. So this is the formula. We know we have these matrices and we have this vector, and those are the weights learned by the model. For those who want to check, these are the dimensions of all these terms, and we can notice that the H that we consider is as a double number of rows because is composed of the two stacked state vector of the bidirectional encoder. Then we have the matrices that project both the vector on a vector which is of dimension n, and we see that the second matrix is taking as input a vector which is 2n. And then data h is not changing the dimensions, and we still have a vector which is n rows. And then we have the vector which does the projection, which is VA, which has these n rows, and when we use it, we transpose it so that the vector is horizontal, and we can do the final calculation to obtain a scalar number. The second step, again, as we said, is just normalization of the numbers, and the relative order is of course preserved, and somehow for numbers that are not too small, we see that the reference are enhanced. So we see here if we have two scores that are 8 and 9, actually when we go through a softmax, we see a higher difference, and the way they are computed is taking the exponential of each of the terms and dividing each of the terms for the sum of these exponentials. And again, the third step is just a weighted sum of all the vectors. So we are using the context vector j. You are using it in the context of the decoder step I. So we use alpha I j, and we take all these weighted vectors, we add them up, and we have this this context vector that, together with the previous step hidden state, will be used by the next cell of our model to derive the new state. As we see here, we have these stacked vector because they are bidirectional, and multiplied by this alpha term, and then we get all of them, and we sum them, and we give it to the model together with the previous state. So now we are at the stage where we have derived this new context vector that is fed to the next step and can be used to calculate, to compute the next hidden state. How is this vector used? We are not surprised that the model is just learning the contribution that this additional input can give. The best way of making use of this representation is learned with some transformations, projections through weight matrices, and these weights of these new matrices will be learned during the training. We use the same approach that we see adopted everywhere. So here in the bottom of the slide, we see how the RNN cells works and how it is computing the next state. We know that we are using a GRU. We know that we have a candidate new state, and we know that we have two gates, and everything is coming from the input of the cell, and learned by some matrices of weights, and from the previous state, and that contribution is also learned by three more matrices. What we're going to have in our new model is that we are going to have one more contribution. So we have three new terms, and for each of these terms we have to learn a new matrix of weights, which projects the new input, the new kid in town, the new vector Ci that is coming into the GRU cell. And the only difference that we see in these formulas is that the input is represented by this quantity instead of x, because this is the decoder, because the decoder is getting the attention term, and the decoder is also getting the input from the output of the previous cell. So this is the embedding. This is step Y. So this is the embedding. This is the output Y. The embedding of the output of the previous step. So I minus 1, because here we have I, and this previous step is I minus 1. So these and these are the same, except for these new terms that with the usual approach allow us to let the model understand, learn, and represent with weights, which is the most useful contribution and which is the best way to exploit the information that the context vector coming from the attention model can give. We know that each cell of the decoder must derive the next input state, but also the output symbol. And the new context vector is used also to derive the output. And we can skip the formulas, but we know that the approach will be the same. The approach is in the formula that derives the output from the hidden state, and the input will also have a new term which is based on the context together with the new weight matrices that will learn the proper contribution that the best contribution that the context can make. So here we will have in the cell three new matrices of weights to handle the attention contribution to the decoder in deriving the output symbol. In describing the various mechanisms and the various pieces of the model that we have been building, we have found everywhere matrices of weights. We have found in every aspect of this big picture, we have found matrices of weights that are learned during training. We have found parameters that allow the model to learn the representations that best handle the input that we are processing, that best produce the results that we are aiming at. And so we have seen that we have in the encoder, we have two RNN, we have a forward RNN and backward RNN, and those are similar models, but they are learning two different set of weights. We have seen weights to learn our embedding matrix, which is also used, to encode the input, but also in decoding the output of the model. We have seen that the attention score is based on weights to learn the alignment scores and to learn which input symbols are most relevant for each particular output symbol. And also in the decoder RNN, which is as the previous ones in these models are gated recurrent units. We have the usual GRU matrices of weights, but we have also added some specific weights to handle the context vector that is coming from attention, and we have some for the next state, and we have some for the output. What we have to take into account is that once we have built all this model that we can represent here, and we can show that we have weights here, we have weights here, we have weights in calculating this, and then we have weights here, and then we have weights here to use the input context. Basically, we have weights everywhere, and these weights are all adjusted together. They are started randomly together at the beginning of the training. So the model is jointly learning all these parameters, and some of them are specifically aiming at translating. So the RNN and the embedding, these are the standard weights that we have in an encoder-decoder translating model, but also we have other weights that are specific to aligning, because aligning means see what is the most relevant inputs, what are the most relevant inputs for each output symbol. So we have the attention score weights, and the weights that tell us how to best handle the context vector for translation. So we jointly learn how to translate and how to align, and this is done at the same time in training the whole model. We now give a look at the improvements that the attention model allowed, what are the results that this kind of innovation made possible.